Welcome to the Pro Tips video series designed to arm biology learners with background knowledge needed to succeed during upcoming lessons. I'm Professor Workman, and this video continues our discussion of chemistry. We will consider the concept of electronegativity and how it relates to chemical bonding. Recall from a previous video that atoms react when the result allows both to achieve a full valence shell. One such scenario is when an atom interacts with another of its kind, and we've seen this example of molecular oxygen, or O2, before. When an oxygen atom interacts with another of its kind, they both face the same challenge, that is, needing to gain 2 electrons to fill their valence shells. This creates a tug of war between equally matched competitors. Both are oxygen, so they have identical strength, an identical tug on these electrons. The result is that these electrons are shared exactly evenly. Electrons involved in these bonds are as likely to be found near one atom as they are to be found near the other. Contrast that scenario with this interaction between the electron donor lithium and the electron acceptor fluorine. In the resulting compound, lithium fluoride, fluorine completely steals away lithium's valence electron. Lithium loses the tug of war, but is quite happy with that result because by losing its outermost electron, it achieves a full valence shell. These examples demonstrate what happens when interacting atoms have either similar strengths or drastically different strengths in that tug of war competition over electrons. This brings us to our first key term, electronegativity. Each element has its own unique strength when it comes to potential tug-of-war battles with other atoms. Revealed through experimentation, this value is called electronegativity. The higher the electronegativity, the stronger the atom's tug on bonding electrons. Electronegativity depends on a couple of factors. It increases when the valence electrons are nearer to the positively charged atomic nucleus, like when magnets are closer together. Electronegativity also increases as atoms get really close to having a full valence shell, like if they just need to gain one more electron, then it's as if they become greedy and strong. Electronegativity values are described by something called the Pauling scale, but that's not important to remember. What is important to remember is that the trends in electronegativity are predictable, and you can look up the electronegativity value of each element. Here are some known electronegativity values. Notice that fluorine has the highest electronegativity. This makes sense because it needs just one electron to complete its valence shell, so it tends to steal electrons completely away from atoms of weaker electronegativity. It is the difference in electronegativity between two interacting atoms that determines where unpaired valence electrons go. These are called bonding electrons because they are involved in chemical bonding. Consider this example. This is our molecular oxygen example that we've seen before. Both atoms are the same element, so they have identical electronegativity. The tug of war is always tied. This means that bonding electrons are shared evenly between the two atoms. And recall that these lines represent each line represents a shared pair of electrons. The next example is H2O, which is water. Because oxygen is more electronegative than hydrogen, it tugs hydrogen's unpaired valence electrons toward it. These electrons hang out near the oxygen's atomic nucleus more often than they are found near the hydrogen's atomic nucleus. In this final example, there is an even greater disparity in the electronegativity of sodium, Na, versus chlorine, Cl. Chlorine is so strong that it steals away the electron completely. Sodium, though, is perfectly happy with this arrangement because it needs to offload that electron in order to achieve a full valence shell. So in this scenario, there is no sharing. That electron now belongs to chlorine. These scenarios produce different types of chemical bonds. When there is little difference between the electronegativity of the atoms involved, a covalent nonpolar bond is produced. This is when electrons are shared evenly. Next, when there is a noticeable difference in electronegativities, the atoms connect via covalent polar bonds. They're sharing the electrons, but they're not being shared evenly. And finally, when the disparity between electronegativities is greatest, the transfer of electrons from donor to acceptor creates a positively charged ion from the donor and a negatively charged ion from the acceptor. Then these ions connect together like magnets. This is called ionic bonding. Ionic bonding is only possible when one or more electrons was completely transferred. This brings us to another key term, ion. Atoms are usually neutral because they have equal numbers of protons and electrons, but electrons can come and go, especially from the valence shell. An ion results from a difference between the number of protons and electrons in an atom because this creates a charge. Ions are charged atoms. Ions can be created in a number of ways, one of which is when an atom interacts with another that differs greatly in electronegativity. The donation and accepting of electrons creates ions in this scenario. Ions are atoms that no longer have even numbers of electrons and protons. In this example, the donor became positively charged because it lost an electron, while the acceptor became negatively charged because it got an extra electron. This interaction simultaneously created two ions, one positive, the other negative. These opposite charges are attracted to each other, and when these ions connect, the resulting structure is called an ionic compound. Sodium chloride is an ionic compound in which the positively charged sodium ion connects to the negatively charged chlorine ion. Whereas ionic bonds create ionic compounds, covalent bonds create molecules. A molecule is a chemical structure comprised of two or more atoms connected via some combination of polar and/or nonpolar covalent bonds, and thus the atoms involved share electrons. Here you can see molecular oxygen connected by one double bond, and below it you can see a water molecule connecting an oxygen to two different hydrogens. So water contains two single bonds. Electrons move around within molecules, similar to moving through an electrical circuit. Molecules that contain a polar covalent bond can exhibit a similar property to a charge. Remember that oxygen is more electronegative than hydrogen, but not strong enough to steal the electrons away completely. Molecules like this, made up of component atoms that differ in electronegativity, are called polar. Polar molecules, like water, have distinct areas within the molecule that carry a slight charge. It's like a weak magnet at each end of the molecule, not even a fully positive or fully negative charge. They're called partial charges only. Even partial charges influence how molecules behave, so this is a special property that is important for biologists to understand. Notice in this alternative diagram of water that the partial charges are represented by a lowercase Greek letter delta, shown here in blue. The red arrows point toward where the electrons are tugged. So because oxygen is more electronegative, it exerts a stronger pull on the electrons and therefore becomes slightly more negative than normal. Conversely, the hydrogens are less electronegative and therefore have reduced access to their valence electrons, which they are now sharing with oxygen. Therefore, the hydrogens become slightly more positive than normal. Any structure that has opposite charges at either end is called a dipole. So polar molecules are dipoles. Atoms are never dipoles, so this ability to become polar is an emergent property of molecules. In summary, you learned that electronegativity refers to an atom's strength of tug on bonding electrons. You learned that differences in their electronegativity values determine the types of bonds formed between atoms. You learned about covalent nonpolar, covalent polar, and ionic bonds, 3 types of bonds. You also learned that ions are charged, whereas atoms are always neutral. And you learned that polar molecules are dipoles, meaning they have partial charges at opposite ends. Thanks for watching. If you liked this video, you might consider watching other videos in the series. Here's my contact information, and I always welcome any feedback. mworkman@pima.edu. Good luck in your biology journey.